Benzene undergoes nucleophilic aromatic substitution as well. When we were talking about electrophilic aromatic substitution, we were reacting an electrophile with the benzene. So the benzene was considered a nucleophile, and you were reacting the electrophile with the benzene. Now here, this is the opposite. Benzene is going to be considered an electrophile, and you are going to react a nucleophile with it. The reaction is going to proceed by substitution, but the reaction is not going to happen unless you have a halogen on the benzene to substitute the nucleophile with. So your product in this case is going to be a nucleophile instead of the halogen. Now, on the benzene, there are conditions. Because on the benzene, you can have either a hydrogen or an electron withdrawing group or an electron donating group. The identity of the group on the benzene will indicate what type of mechanism you are going to go by with the nucleophilic aromatic substitution. So there are two types of mechanisms for this reaction, and the types of mechanisms depend on the temperature of the reaction, and they depend on what the groups are on the benzene. Now, for both, you would need a halogen on the benzene because after all, you are substituting the halogen with the nucleophile. The two different mechanisms are addition-elimination and elimination-addition. The nucleophiles used for both, they are the same. The difference is in the temperature, and again, as I said, in the groups that are on the benzene, and this is what's going to indicate whether you're going by addition-elimination or elimination-addition. Since it is a substitution reaction, we need to use a good nucleophile in there. And the good nucleophiles for these reactions are sodium amide. Now, for sodium amide, we know that sodium is positive charge, so the NH2 is going to be a negative charge. Okay, the nucleophile that we want to use needs to do a double job. It needs to be both a good nucleophile and a good base. This is why all of the nucleophiles that I'm listing over here, these are strong nucleophiles that can act as a strong bases as well, because the mechanism is two parts. You start by addition, you do elimination, or you start by elimination and do addition. So you need a nucleophile for the addition, and you need a base for the elimination. And these act as both nucleophiles and bases. They are good nucleophiles and good bases. So let's start with the addition-elimination reaction. With the addition-elimination reaction, now we said that the halogen is a must. So you would need to have a benzene and a halogen on it. This is what is substituted by the nucleophile. Now, in addition-elimination, you would need to have an electron withdrawing group on the benzene. This is a must to have. So electron withdrawing groups, they need to be on the benzene. And they need to be on a specific position, ortho or para or both. So here I have an example of the NO2 being ortho and para to the chlorine. NO2 being ortho to the halogen and NO2 being para to the halogen. These are the three cases where you start with addition-elimination. So again, whenever you want to start with a nucleophilic substitution reaction, you would need to look at your benzene, and you would need to look at the groups that are on the benzene. The groups on the benzene, they need to be electron withdrawing groups, and they need to be on the ortho and the para position, not on the meta position. Because if you have an electron withdrawing group on the meta position, then the mechanism is going to be elimination addition. Since you are substituting the halogen on the benzene, so the more electronegative the halogen is, the faster is the reaction. So if you are starting with a bromine, it's better than a chlorine. If you're starting with a fluorine, it's better than a bromine, it's better than a chlorine. Also, the more electron withdrawing groups on the benzene, the faster is the reaction. So here I have an electron withdrawing group on the ortho position. This reaction is slower than having two electron withdrawing groups on both the ortho and the para position. They have to be on the ortho and the para and not the meta position. This is the general reaction in there. You know that this is an addition elimination because always you look at your electron withdrawing group. If you have it on the para or the ortho, then this is going to go by an addition elimination. And then you have your leaving group in there. This leaving group is the group that gets substituted by the nucleophile. So here I'm using this nucleophile. I can use other nucleophiles. I can use NaOH. I can use NaOR. So any of those nucleophiles that act as bases. The R can be either a methyl group or it can be an ethyl group or any other R. But we don't use bulky bases because after all you are doing a substitution reaction. If you use the OH, if you use the sodium hydroxide, then you are replacing the chlorine with the OH. If you use the OR, then you're replacing the chlorine with the OR. It's very important when you are drawing the mechanism of the reaction, make sure that you draw the loose structure of the NO2 because resonance is going to happen across the ring in there. The intermediate in this reaction is a carb-anion intermediate. And the reaction starts by addition, and then it's followed by elimination. So as the name says, addition, this means that I will be starting with my nucleophile, and the nucleophile is going to come and add to the carbon that has the leaving group. Okay, this is an sp2 hybrid carbon, and it goes by different conditions than the regular substitution SN1 and SN2 that you know. So the nucleophile here, it's a strong nucleophile. It's going to come and add to the carbon in there. Now, when it adds to the carbon, the chlorine won't leave. Elimination will not happen like this. Elimination will happen after the negative charge is distributed across the whole structure, and then the final step, resonance is going to happen and the chlorine is going to leave. So the first step, you create a carb anion. The NH2 is going to add to the carbon, and then the negative charge is going to be on this carbon by opening the bond. Now, once the negative charge is formed, you will end up having resonance stabilized intermediates. The resonance stabilized intermediate will have the negative charge distributed on this carbon, on this carbon, and on this carbon over here. Notice that the negative charge that you are forming in here is in the ortho position and in the para position of the halogen. It is very stable. This is why the electron withdrawing group has to be either on the ortho position or on the para position. It cannot be on the meta position because the negative charge during the resonance stabilization, it will never be on the meta position. So once the negative charge reaches this carbon over here, elimination will happen. And the elimination will happen to regain the aromaticity of the ring in there, and then you are going to end up getting your product. Let's have another example here. First, you look at, you make sure that your halogen is there, and then you look at your nucleophile and make sure that your nucleophile, which is the OCH3 in this case, this one needs to be both a strong nucleophile and a strong base for the reaction to happen. And then last, you would need to look at your electron withdrawing groups and make sure that they are either or on the ortho or the para position. So the NO2 here is on the ortho and the NO2 here is on the para. They should not be on the meta position for the reaction to happen. So here the reaction is going to proceed by addition, elimination. Mechanism of the reaction, step number 1, you are doing addition followed by elimination. So for addition, this means that the reagent that I am using is going to act as a nucleophile. So the reagent acts as a nucleophile and it's going to start by adding to the benzene. So when it adds to the benzene, it's going to add on the carbon that is connected to the halogen. Okay, make sure you draw the Lewis structures for the electron withdrawing groups. That is very important when you are doing resonance, just to see the resonance stabilization of the carbon. So you have your nitrogen over here. This is going to be a double bond O. Okay. So here you go. This is a negative. This is a positive charge. NO2 has a 0 charge. So we're going to start the reaction by having our nucleophile, which is the OCH3. This is going to be the OCH3 negative. This is going to come and attack. That is a negative charge. This is going to come and attack this sp2 hybrid carbon. What helps it in the attack is the electron withdrawing group on the rings. Okay, so when it attacks over here, the double bond is going to open up and form a carbanion, a negative charge on this carbon. That negative charge is going to be stabilized by the NO2 in there. And then we're going to do the resonance stabilization across the structure. So you have your fluorine. The fluorine is going to stay. It's not going to be eliminated until the end. So you added your OCH3 in there. You formed your carbanion, and this is your intermediate. This is the double bond O. This is the oxygen. This is positive, negative. And as I said, notice that the carbanion is on the carbon that is attached to the nitro group. This is going to make the structure very stable. Let's go ahead and put our double bonds in there. So you have a double bond here, you have a double bond in there. This is a resonance stabilized intermediate because after all, you broke the aromaticity of the ring. So your intermediate has to do resonance in order to compensate for the stabilization. And there, let's put all of these intermediates in brackets, and let's go ahead and do the resonance in this case and circulate the negative charge. I missed the NO2 over here, so let's go ahead and put that. This is the oxygen and the O, negative and positive. You're going to form your negative charge on this carbon, and again that will be resonance stabilized because it is adjacent or on the NO2 group. So you have your NO2 over here. This is going to be positive, and now this carbon over here is going to be a negative charge. You have a double bond. Resonance is going to keep happening until you reach the carbon adjacent to the halogen so that the halogen can leave. So here you go, you have your fluorine, and now your negative charge is going to form a double bond here, and the double bond is going to form a lone pair and the negative charge on the adjacent carbon. So you're going to end up having a negative charge here, a double bond, and another double bond. Don't forget your NO2. So I have an NO2 over here, and I have an NO2 over here. Okay, and this is my NO2 as well. The last resonance structure is going to regain the aromaticity of the ring and allow the halogen to leave. And then you are going to end up forming the aromatic ring back again. But now what you did is you substituted the fluorine by the OCH3. Everything else stays the same. So the NO2 stays in positions both on the ortho and the para position. Again, we need the electron withdrawing group to be either on the ortho or the para position because the carbon ions, all of those are carbon ion intermediates. So all of those are carbon ion intermediates, and the carbon ion is always stabilized whenever the negative charge is directly connected to the NO2. And the negative charge is directly connected to the NO2 when it is on the ortho position and when it is on the para position. There is no negative charge on the meta position throughout the whole resonance to stabilize the structures in there. This is why NO2 is not supposed to be on the meta with addition elimination. The second type of nucleophilic aromatic substitution is elimination addition. In this type of reaction, you start with a benzene, and the benzene should have either an electron donating group or an electron withdrawing group on it. Of course, you need to have your halogen in there. So the halogen is a must because this is where you're doing the substitution. If you have an electron withdrawing group, the electron withdrawing group has to be on the meta position. It cannot be on the ortho or the para because that is specifically for addition elimination and not elimination addition in there. So electron donating groups, these are criteria for elimination addition and not addition elimination. Electron withdrawing group, if present, has to be just on the meta position. Other than that, we can use any of the bases and the nucleophile that we used up there. But if you use NaOH or if you use NaOR, then with these two nucleophiles, you would need to use heat with them. With sodium amide, you don't need to use any heat. Ammonia normally is used as a solvent whenever you use this nucleophile. The reaction here is going to proceed by forming a benzyne intermediate. So up there, we had a carb anion intermediate. Here, we have a benzyne intermediate. Let's have an example in there. So this is an example where you have no group at all on the benzene. You have a base. Whenever you're using the nucleophile NaOH or the base in there, make sure that you use the heat. With both NaOH or NaOR, you would need to have high temperature, more than 300 degrees Celsius in there. The reaction happens in two steps. The acid here is just to make sure that the reaction will proceed to completion. And here you are substituting your halogen with whatever nucleophile that you are working with. So I'm working with NaOH, then it's going to be NaOH. If it was an NaOR, then this one is going to be NOR. With these types of reactions, if you have a substituent on the benzene, then you're going to end up getting two products in there because of resonance due to the intermediate. We're going to go over the mechanism for the reaction. Here you have an electron donating group on the para position. Again, the electron donating group can be anywhere on the benzene. And I'm substituting the halogen with the NH2 in this case, and the NH2 is going to be assumed two positions, either on this carbon, which is para to the CH3, or on this carbon, which is meta to the CH3. So you're going to get two products in this case. If NO2 exists on the benzene, that it needs to be on the meta position. And for this type of reaction, we're going to end up getting two products in there. The mechanism is a must because since you're getting two products in there, you need to do resonance to know on what position the NH2 is going to add. Here in this case, it's adding ortho, but it's not always going to be the same. It really depends on the position of the halogen where it is. So you're going to have the ortho and you're going to have the meta product. Let's start with the mechanism of the reaction. So you're having your NaOH. The first step is elimination. So if it is elimination here, I'm using the OH as a base. And we know that bases, they will take the hydrogen. Always the bases take the beta hydrogen. So let's label our hydrogens in there. This is going to be the alpha carbon. This is going to be the beta carbon. So on the beta carbon, you have the beta hydrogen. So the base is going to come and take the beta hydrogen. When it does, you're going to form a negative charge on the carbon. This is not the intermediate, okay? The intermediate is going to form directly after the negative charge is formed. And by resonance, you are going to do elimination to kick out the chlorine. This is the first step. So the first step, base comes, takes the hydrogen, form a negative charge. Elimination immediately happens and the chlorine is kicked out. So what you have here is a benzyne intermediate. This is a triple bond. This is why I'm ending the name with Y and E. The structure is completely unstable because imagine like putting the triple bond in a cycle. We know that the triple bonds are linear. They are 180-degree bond angle. So when you want to squish the triple bond into the benzene, this is going to result with a completely unstable intermediate. That intermediate will not stay stable long. It needs to do resonance in order to get rid of the triple bond in the cycle. So after you do the elimination, now you are going to do the addition. So after the OH now acts as a base, takes the hydrogen, makes the triple bond, then the OH is going to attack again, and now it's going to act as a nucleophile. But you can notice here, for this example, it really doesn't matter because those two carbons are the same. I don't have any substituent on the benzene. But if I have a substituent on the benzene, the OH has the possibility to attack either this carbon or this carbon. And this is why we get two products and not one. So the OH now is going to come and attack the carbon of the benzyne. So it's going to attack the sp hybrid carbon over here. Either one of these carbons, in this case, it doesn't matter because both are the same. If they are not the same, then it's going to attack each one of them separate to get a different product. So the nucleophile now is going to come and add. So this is now your addition. Form a negative charge on this carbon, and that negative charge is going to be protonated. This is why in these reactions in here, we need some sort of a solvent that has a hydrogen. So the solvent can either be H3O plus, it can be ammonia. Any solvent that has a hydrogen can do the job in there. Water, for example, whenever you use sodium hydroxide is dissolved in water. So always assume that water is there in the solution. The negative charge is going to come, pick the hydrogen, and you're going to end up getting your product. Let's go ahead and have another example over here. So you have your CH3 that is paired to the chlorine electron donating group. Then immediately I know that this goes by elimination addition. Elimination, I'm going to start with this as a base. So the base is going to come and is going to take the beta hydrogen. It's going to form a negative charge that is going to kick out the chlorine by resonance. And I'm going to end up getting my benzyne intermediate. Once I form the benzyne intermediate, now notice here that I have two positions for the carbons of the triple bond. I have this position over here and this position over there because of the presence of the CH3. It matters if the NH2 attacks meta to the meta here, to the CH3, or if the NH2 attacks para to the CH3. So this is why you need to consider both. Let's consider the first one where the NH2 attacks on this carbon, so it will be para to the CH3. You will form a negative charge that gets protonated with any solvent that has a hydrogen, okay? Any solvent that has a hydrogen, and you're going to end up getting your product. Also, it can attack on the adjacent carbon of the triple bond, form a negative charge here that gets protonated by the solvent, and you are going to get the meta product. This is another example, but with the electron with the drawing group on the meta position. Okay, same thing. You choose always your alpha carbon where the halogen is. This is going to be your beta carbon. So the base is going to come, take the beta hydrogen, form the negative charge that's going to do resonance and form the benzene. Once you form the benzene, you have two positions where the NH2 as a nucleophile is going to act, either here or here. Practice the mechanism because you are responsible for it. And you're going to end up getting both negative charges that you are going to protonate in order to get to the product in this case. There are additional examples in the problem set. Please practice those.